All right, so some people overthink this chapter. It is really the reverse of chapter 7. In chapter 7, we went from an alkane and we made a double bond. Now we're going from a double bond and making a alkene with the halogen or leaving group attached. And so this table here, take a picture of, memorize it. It is what it's the primary thing that'll give you the major products. So to explain Markovnikov addition, the electrophile is going to be added to the more substituted side. So the carbon that is more substituted, the often halogen is going to be added to that carbon that is more substituted. Anti is the reverse. Syn and Anti-addition, cis and trans, basically the same thing. You have your hydrogens or you have your halogens. They're added in the same direction, and that is syn. If they're added in different directions, it's anti. So given this table, that will basically give you a guide to where things are going to be attached. Here's your reactions for this chapter, and I broke them down into the types. So hydrohalogenation, oxymercuration, and halogenation, they all add to the more substituted side. And you have hydroboration, in which it adds to the less substituted side, and these are just outliers. I would flashcard this chapter, and what I mean by that is you have so let me just give an example. So you have a reagent, you have your double bonded compound, you have your reagent. So your reagent will tell you what kind of reaction is going to take place. So you have your reagent, you have an H halogen, so this is going to be a hydrohalogenation. And with that, you know that the halogen is going to be added to the more substituted side. Make sense? That's how I would flashcard it. That's what I did when I took this class. And so, using those rules, we know that I'm going to break down this first example. So this pi bond is extra electrons are going to attack there. That is going to dissociate, and so you have, wow, that's sucky. Br floating around. You have this intermediate, and that Br will act as a SN2. It will act as a nucleophile or a base and come in at an attack, and your final product will be that. So it's really that simple. So hydroboration, if you have an H halogen, you're going to be dealing with a hydrohalogenation, which means that the halogen is going to attach to the more substituted side. So if you look at this, if you look at the double bond, which side of the double bond is more substituted, that's where the halogen is going to attack. An anti-Markovnikov is just the opposite. If you have an anti-Markovnikov reaction, which is the less substituted, or react to the less substituted side of the double bond. So using that logic, you should be able to see that this will, so going back to the last chapter, you'd see that your intermediate would be like this. And we know that this is less stable, and here's a ring with a ring strain, and so it's able to go to a more stable cycloalkane, and so it's going to do a ring expansion. Upon your ring expansion, you'll end up with something like this. And when you have your hydride shift, you're going to have something like this, and now the Cl will come in, and we see that the product, the Cl, will be added to the more substituted carbon. Simple as that. Also, if you have an acid, if you have just a proton, if you just have an H ion, or you have a heavy water, Christy, yeah, basically the reverse of chapter 7. If you have if you have H3O, it's an acid. Anything with a positive charge, we know from acids and bases that's predominantly going to act as an acid. And so if you have something like these, it's going to be an acid-catalyzed hydration, and you're really just going to be adding a OH to, again, the more substituted side. So you should be able to figure out that the product for this one will be like that. Exactly, as we can see, the same rules apply. The H, this will react with that. You have H, and you have the extra electrons on the water, which will then attack to the more substituted side. So again, if you're given these reagents, if you have an H with a halogen, or you have an acid, it's going to undergo hydrohalogenation and or acid-catalyzed hydration. Your halogen will be attacking the more substituted side, which is Markovnikov. Okay, again, given this table. So you should be able to see that this product will be Does that make sense to everybody so far? The two of you that are here. All right. So again, just because I categorized these, I'm going in order. The next Markovnikov related addition is Oxymercuration. So if you have a mercury, you're going to, again, it's intuitive. You have a mercury, you're going to be dealing with an Oxymercuration. And at the end of the day, don't complicate it. You're adding an OH to the more substituted side. So your product will be like that. In the my previous section, somebody asked me to break it down. So just to give you that, you're going to have that double bond. It's going to react with your mercury, and the water is going to be attacking the more substituted side. And so you create, so bonds being made, bonds being broken, you're going to be making this mercurinium ion. And this Na will dissolve away, the BH4 will come in and simply take away the mercury. So the water that's flowing around will come in and attack the more substituted carbon, and you know that it's going to break. This bond is going to break, and therefore you get something that looks like this. The BH4 will act as a base because, again, the Na is dissolving away. NaB4 has those extra electrons where it can attack there and take away this. So really, you're just left with that. That's the I broke down, this is just the breakdown of the mechanism. But at the end of the day, when you have a mercury, you're dealing with mercuration, demercuration, and at the end of the day, you're just adding a OH to the more substituted side. So using that logic, you should be able to visualize that your product for this reaction, your OH is the more substituted side, which is this carbon here. Boom. That is it. Everybody get that? All right. Next up is halogenation. So again, if you're just given a diatomic halogen, you're dealing with halogenation, and you know, if you're going to flashcard it, that halogenation undergoes Markovnikov, and memorize that halogens will be added anti, and anti is trans, so they're just going to be added in the opposite direction. So this example here, you should be able to visualize that the double bond is where they're going to attack. And so just because, you know, there isn't really another option, these are the only carbons that you're going to be attacking. Sorry, it's my mom's phone. Just answer it. So again, the halogens are added in the opposite direction, so you could draw it like this, or vice versa. So hopefully that makes sense. This one, again, it should be intuitive that it should be intuitive that they're going to be added in the opposite direction, and so you're going to be dealing with one of them being wedged, one of them being dashed, or vice versa, right? But if you have your diatomic halogen and water, you're going to add one halogen and you're going to add one OH.
So that would be cute, I think, right?
All right. And the water versus the halogen, the OH is going to predominate. The OH is going to predominate and attack the more substituted carbon. So if you have a diatomic halogen and you have your and you have water, you're going to be adding the OH to the more substituted side, and your halogen to the other. That will be a product. And again, just to visualize the anti-addition, one can be wedged and the other can be dashed. Does that make sense? All right, so your anti-Markovnikov additions. So your anti-Markovnikov, again, is just the opposite of Markovnikov. You're going to be adding the something to the less substituted side. And again, just flashcarding, if you're given this reagent, if you're given BH3, you're going to be dealing with hydroboration. All right, so you're adding an OH to the less substituted side. And so looking at this example here, you have this carbon and this carbon. Is the left or right? Is the left or right carbon the less substituted side? The right. So you know that as simple as that, your product will look like that at the end of the day. Somebody asked to break it down a little bit. In which I don't mind doing. So I'm just gonna see if I can. All right. So with these, the reaction, and so really it's gonna. You have this big alkyl-borane intermediate because it's reacting twice really. So you have, so their mechanism is going to look like this. You have your H, pH, that is how you get right. And again, they're added in the same direction because this is adding in the syn and, or if you want to call it cis formation. So because this has these other hydrogens, it can do this 2 more times. And so your big alkyl borane intermediate will look something like this, all right? And that 2 more times. And really, if you're given, I wanted to pull these up. If you're given the alkyl borane intermediate, simply, let me zoom in. Simply break the first bond, and what you're left with is what you started with. So he could give you the alkyl borane intermediate and be like, what was the alkene that we started with? Simply break, and that is what you started with. Does everybody see that? All right, so without going through the big mechanism, you should be able to see that. Again, you're given the BH3, you know that it's going to be hydroboration, you know, and therefore you know that your OH is going to be added to the less substituted side. And so product for this will be like that. Moving along with our other just outliers. So with these, you're not really going to have to worry about Markovnikov or anti-Markovnikov. It's just really going to be syn or anti. And so if you're given an OSO4, you know that it's going to be dihydroxylation. What that means is you're going to be adding 2 OHs. So dihydroxyl, so 2 OHs, and you're going to be adding them in the same direction. All right, so you should be able to visualize that simply, again, this same direction, so we can just ambiguously make them wedged. Right, so dihydroxylation, you're given your OSO4, you know it's going to be dihydroxylation. You added your 2 OHs, and they're going to be adding in the same direction. That's why I drew them both wedged, or you can draw them both dashed. And another reagent that can do this is cold dilute KMNO4. Okay, keep in mind that it's cold. There's another reaction that can do hot KMNO4, but dihydroxylation can happen if you have cold KMNO4. All right. So for the bottom example, again, you're just adding the 2 OHs in the syn formation, so in the same direction. So you could have them both dashed or both wedged. Here I'm just drawing them both dashed. All right. Does that make sense to everybody? All right, we are moving. I'm going to get it on time. So, ozonolysis, if you have ozone, again, do your flashcards. If you have ozone, you know you're going to be dealing with ozonolysis. And all you have to do is okay, first and foremost with this, you're not going to have to worry about cis or anti-addition. You're not going to have to worry about Markovnikov, anti-Markovnikov. Simply split the double bond in half. So therefore you get this, right? You split the double bond in half, and you simply add an oxygen to the inside ends. So your two products you're going to get from this are simply that, carbonyls. Right? And that is ozone with this dimethyl sulfate. And in case he throws it out there, this is a reductive reaction. Reductive. If you have ozone with acetyl OH, it is oxidative. That's why you're going to end up with a product that looks like this. So again, just split your double bond in half. So for this, you would get, if you split your double bond in half, you would get these two things here. But again, going back to our Gen Chem, what do we know from oxidation? You're dealing with oxygens, and so you're going to have one, and again, this is a carbon here, but you're going to add another O, right? So these are your two products for this oxidative ozonolysis. So you have your oxidative ozonolysis and you have your reductive ozonolysis, and the difference between them, when you're choosing between them, look at what the ozone is with. So again, just split the double bond in half, add your O's. And unlike the cold KMnO4, which is dihydroxylation, if you have hot KMnO4 ozonolysis, it does the same thing as these. Everybody get that? All right. So another thing I want to throw out here, he may or may not give you guys an example of this, but just in case, I'll have this thing. It's just an extra, but it's something called cyclopropanation. And again, just using the same reagent as last time. You have your alkene, and what do you think is going to happen if you're cyclopropanating something? Right? You have a cyclopropane that you're going to end up with. So what's going to happen is simply go from where the double bond is, make a triangle. Your product will look like this. Halogen, halogen, given that the reagent, a lot of times you're going to see it as CH. Let me just say, okay, halogen 2. So CH dihalogen. This is how it's going to form. So you're adding your two halogens at the tip of your cyclopropane. So again, simply just, if you're given this reagent, CH, some halogen, let me just say I, so CH, two iodines, you're going to be making a cyclopropane where the double bond was with your two iodine. Also, another one that does this, so another reagent is CH2 right, with zinc or copper, I believe that is. So when this happens, the same thing is going to happen, but you're not going to end up with the product that has halogens on it. You're simply just going to make the cyclopropene. All right, it's simple as that. And I bring up this reagent because this CH2, you might ask about it, is something called a carbene divalent ion, which looks like this. That's just a side note. So this is carbene. All right. So does that make sense to everybody? Cyclopropanation? All right, perfect. All right, that is all of your reactions for this chapter. Again, simply don't overthink it, flashcard them, and feel free to take a picture of this as I categorize them. All right. So hopefully that helps you guys. I know in SI, I did these examples because in SI he did things really simple, like all of the reactions are going to be with that or something similar. So I wanted to give you guys examples that you're more likely going to see on the exam and or bonding. So again, simply use this here and you'll be set. Flashcard and remember the rules and apply them. Simple as that. So that is all I have for you today. And I will stay back for a few minutes in case you guys have a few extra questions, but that's